Okay, so I'm very happy to give this series of 3 lectures. In fact, it was I gave a master course in Paris in this semester. Some students are here. So it was 12 lectures. So now it's becoming 3. So I tried to compress all the things, but I had some difficulties, in fact, to do this job. So we will see what is going to become now. So the topic I would like to cover is, in fact, is the topic of, as the title indicates, so understanding monodromies of holomorphic families of Riemann surfaces, and in particular and especially the algebraic families of curves. And in fact, it is there is not at all originality in the point of view. In fact, I'm just following a very nice article or preprint by Macmillan, and I wanted to understand, and to follow this point of view, which is called it's 98 or 99 paper. It's called From Dynamics on Surfaces to, I think, rational points on curves. So probably I will have the opportunity to justify this title in the course of the lectures. But in fact, the subject is the following. So the subject is to take, so what is the definition of a holomorphic family of Riemann surfaces? And in this course, these Riemann surfaces are going to be compact or eventually of finite type, namely compact Riemann surfaces minus a finite number of points. But in general, the definition is the following. So we have a family of Riemann surfaces xb, so depending on the parameter b. And here, b is in the lectures is going to be a complex manifold, and in fact it will be a Riemann surface. So B is a Riemann surface called the base, and we have to define what is the meaning of holomorphic. And in the following definition, I'm going to follow the point of view that was given by Kodaira in his deformation of complex manifold theory. And so what we do is that we put B below. So here's the Riemann surface, and we're going to think of the Riemann surface as something which is above B. And so the definition is that we are going to have a space which is an analytic space here, which is a union of all these Riemann surfaces of our family. So this space is going to be denoted by X. So in our case, it's going to be a complex surface. And we have a holomorphic proper summation, X to B. So this is the data, in fact, of a holomorphic family of Riemann surfaces, and our Riemann surfaces xb is just the fiber over B, right? So this is the definition of what is a holomorphic family of Riemann surfaces. So namely, if the meaning of holomorphic means that you can build such a complex surface, which is together with this submersion, in such a way that your Riemann surfaces in your family are the fibers of this holomorphic submersion. So this is really the point of view of Kodaira's deformation theory. Let me just give some examples. So, first of all, you have plenty of examples coming, for instance, as you know, in the theory of pencils. If you take, for instance, first example I would like to give is, say, pencils of, everyone knows that, conics passing through 4 points, for instance, in the plane. So here I'm going to consider complex things. I'm going to consider affine plane or projective plane, complex plane. So you take 4 points, and you can draw all the conics passing through these 4 points. Of course, you have some smooth ones like this, but you also have some singular ones. For instance, the union of 2 lines passing through these 4 points are also form also a conic, right? So you have 3 of them, so like this. And then you have also some, in the complex space, you don't really do the difference, but you have also some hyperbola. Yeah. And all these conics gives fill your complex projective plane. And in fact, you can think of the family of all these conics as being holomorphic family of curves, because so here the x is going to be so the projective plane, but you have to do some modifications to really get the definition that I just wrote here on the board. First of all, in a pencil, you have base points, namely you have points where all the curves are passing through. So here you have 4 base points. And what happens is that if you make a blow up at these points, so you construct a new complex surface by replacing the points by a projective line, which consists of all the directions at these points. So then you get a new complex surface, and the pullback of your pencil becomes without base points now. And also here, I'm considering really Riemann surfaces, so smooth objects. But here you have singular ones. So in fact, you have 3 singular objects here, 3 singular conics. So if you just take this, so this complex surface is just a blow up at base points, and you take out the singular curves, so conics here, and you get a complex surface. And in fact, as you know, a pencil of curves is parametrized by the Riemann sphere, so the projective line. And so you get a map from P2, the projective line, which assigns to a point the point in the projective line corresponding to the curve where you lie, right? So you get a map to X to this complex surface to the projective lines, and you have to take out the values corresponding to the singular conics. There are there are 3 values corresponding to singular conics. And in fact, of course, I did the picture for conics, but you of course can do for cubics. So you have to consider more points or quadrics, etc. And then you get more interesting families, because in a sense, this family I just drew on the board is really trivial in the sense that you probably all know that a conic is always a rational curve, meaning that it is biholomorphic to the Riemann sphere. And so as a family of holomorphic curves, you just get the constant curves. So it's really a kind of trivial examples from the point of view of varying families of Riemann surfaces, but still, but if you complicate the situation, you consider cubics or quadrics, etc., you will have, by these procedures, very interesting examples. So another example which is kind of similar, just to give that. So suppose you take a complex projective surface inside, say, P3 of C. You can be more general, but just to fix ideas. And I'm just going to suppose it is smooth. So you have a kind of surface here, complex surface in the projective space now, right? And so what you can do is you can consider a line, delta, and look at all the hyperplanes that contains delta, the planes that contains delta, right? So it defines a pencil of planes of the space. And now you can intersect these pencils of planes with your surface to get a pencil of curve on the surface. So I don't know, it's kind of hard to do the picture here, so maybe it's going to be something like that. And so you get a decomposition. I mean, you get a pencil of curves on your complex surface, which is completely analogous of what we had for the complex projective plane. So say S is a complex surface. So now you make your plane moving, and you get a lot of varying. So you get a family of curves that is holomorphically in the same sense. So you have to do the same operation that we did before. So for this pencil of curves, you have some base points, so points where all the curves pass through. So you have to blow those points, and also you have to take out the singular fibers to get a complex surface. And for this complex surface, you will have a map, holomorphic map to P1, such that the fibers of this map are the curves of your pencil, right? So you have plenty of examples coming from, say, algebraic geometry, and okay, so okay, so in fact, this, if you take two of the conics, so say C1 and C2, right? So this is the theory of pencils. So take two of the conics, C1 and C2, right? They have two equations. So they are defined by Ci is equal to Ei is equal to 0 for some polynomials of degree 2, where the PI's are degree 2 polynomials. And these degree 2 polynomials vanish at these 4 points, right? So what are all the conics that vanish at these 4 points? In fact, they are linear combination of these two polynomials. And so any of the conics appearing here is something like T P1 plus P2 is equal to 0. Where T is a complex parameter, right? So now the map is just, say, maybe I was just maybe put a minus here. I think the map is going, the map to P1 is just going P1 over P2 or something like this. So it assigns to a point the t parameter corresponding to the conic containing your point, right? So I think this t parameter is going to be, so it's going to be p2 over p1 in that example. So the function here is p2 over p1. This is a rational function, right? This is a quotient of two polynomials. And so it has some indeterminacy points. In fact, this function a priori from p2 to p1 is a rational function. There are some values where it is not defined, but we have taken out the base points corresponding to these indeterminacy values.
So you're using the fact that 5 points determine the conic, 5 distinct points determine the conic.
Right.
To get a map from C2 to get your map pi.
Right, exactly.
And you're also implicitly you're using the fact that if you have 4 points together with a tangent line at one of those points, that also determines the conic, right? That's why you're blowing up the singular points.
I didn't get the last one, so you say?
But so you've also done the blow up.
Right.
And that's because 4 points together with a tangent line at one of the points.
Oh, yeah, right. I see.
I'm trying to recall the algebraic geometry.
Exactly.
I don't know.
No, you are completely right. If you have the direction, if you have a point which is not one of these 4 points, you are right. There is a unique conic passing through these 5 points. But if now you have 1 point plus a direction, which means an infinitesimal, so if you have a direction, you will have a unique conic passing through that point with this direction. Right.
Sorry. So that x means to that time. So could you please point where's the pencil in your
Here?
X is the pencil?
Yes. So no, x is the surface, right? So x is a complex surface, and this complex surface, in fact, you can lift the conics here to this complex surface. You take the transform by the blow-up of the curves, right? So in fact, at those points, it was related to the question of John. At those points, you just lift the direction of the. So over one of these points, you have the set of directions, and you lift the curve together with the direction at those points, right? You get the strict transform of the curves. And these strict transform of the curves form a partition of this x, right? And you also have this function p2 over p1, which now is well defined on this x. And this is a function pi that we use to speak about family, holomorphic family of curves. So let me just say something which is interesting here is that, in fact, so what is going to be the goal of my, so it was just to give you some examples. So you have really plenty of examples of holomorphic families of curves, which in this case is algebraic families of curves. And now my goal in the lecture is going to approach the following result, which is called, I don't know if there are some. Okay.
Your last example shows that any surface can appear as a pencil.
So any surface contains a pencil of curves. Any algebraic complex surface contains a pencil of algebraic curves. Right. Yes, but there is a subtlety because you have to take the blow up at the base point. But so every surface has in its so it has a is birational to a surface having a really a family of algebraic curves as in the definition, right? Yes. Sorry. Yeah, so in fact, suppose you... Yes, so in fact, you can do that construction with a base which is not a curve, but a complex surface. Say B, you can do the same definition with a B which is not a complex, which is not a Riemann surface, but say a complex surface. And now you take in B some variety which is not holomorphic, right? And this is just, that will give you an example of a holomorphic family of curves which are not holomorphic, right? Okay, so the goal of my lecture is going to go through in the direction of proving what is called the geometric Mordell conjecture, which is now a theorem. I mean, it's a theorem from a long time ago. Because if I understand well, it was proved by Manin in the 60s, I think. Which is that suppose XB is a holomorphic family of Riemann surfaces of genus, so compact Riemann surfaces of genus G larger than 2, where B is a finite type Riemann surface. Right, then there is only a finite number of holomorphic sections from B to X. So this means that there is only a finite number of ways to determine a point in a fiber of this fibration, or a point in the Riemann surface, depending on the parameter B, and depending holomorphically on this parameter. Right? And why is this called geometric Mordell conjecture? Because in fact, it is really a kind of the analogous of the Mordell conjecture, which is arithmetic Mordell conjecture, which says that on a curve defined over a number field, smooth curve defined over a number field of genus larger than 2, there is only a finite number of rational points, right? And in fact, if you look, for instance, at this example here, you see well why this is related to these two statements are related, because so say S is given by, so in that example, S is given by P of U V W is equal to 0, and assume that the pencil of hyperplane passing through delta is given by just W is equal to constant pencil of hyperplanes. So here the line delta is in these coordinates is going to go to infinity, right?
So if you fix one genus to a Riemann surface, you take the trivial family over one.
Right.
I'm
Right. This is a very good remark. So you are completely right. So of course, in that example, you have an infinite number of sections. You are completely right. So you take just a point is equal to a constant, right? So I just missed a hypothesis, which is here a truly varying family. So namely, you want that you want that the modulus of your curves is not constant, right? So you're completely right. So I come back to this just to make the analogy more clear. So let me see if I have some. Yeah. Okay. So yeah. So assume that your pencil of hyperplanes is given by W is equal to constant. So it is say horizontal hyperplane is these coordinates u, v, w. And so now you write your polynomial. So what means to find a section here is just this means that we can find a rational function of w, so u, or at least holomorphic function of w, u of w, a holomorphic function of w, v of w, such that this equation is satisfied, right? So, so of course, if you write your polynomial as just say, just yeah. So I'm considering this polynomial as being so a polynomial in the UV variables, but with coefficients in the ring of polynomials in the W variables. And so in fact, in these examples, finding a section is exactly finding a rational point, namely a pair of rational function in W, U, V, such that P of UV is equal to 0, right? So this is exactly finding a rational point on this algebraic curve, P is equal to 0. So this is why it is called the geometric model conjecture.
Can you go over that again, please?
Yeah. So finding a section. So the base is a W. So W gives you the function which defines the pencil of hyperplanes, right? And so finding a section means that to every W you want to find a point UW, VW lying on your curve, or defined by PU VW is equal to 0. So finding a section is the same as finding holomorphic functions U of W, V of W, such that P, U is equal to 0, right? And so this is exactly the same thing as for this polynomial considered as a polynomial in UV, but with coefficient CW. This is exactly the same thing as finding a rational point, right? So yes, I think so. I don't know. I mean, I cannot say, but I think there are some results where you get some effective. But yeah, we'll see. I'm going to try to answer you maybe tomorrow. I'm really thinking tonight about that. Okay, so what was, in fact, I should tell you that I am not really interested in that statement, but more in the fact that to prove that we use monodromy, and we study the monodromy representation associated to a holomorphic family of curves. So let me just tell you that if you have a holomorphic family of curves, so this pi is locally a fibration from the differentiable point of view. And so you can, if you fix the base points, you can try to follow the, and then you make it.
C of W question.
Yes. Yes, this is rational related to this ring C of W, right? This is not rational in the sense of Q points. Of course, this is the reason why it is geometric. It is related to ring of functions, not ring of. Right. So I was saying that, yeah, so if you fix a base point and then you make a loop in the base space, so then you can follow by continuity and using the fact that it is a vibration, can follow, take along this loop a trivialization of the vibration, but then when you come back, you get a certain diffeomorphism, which is well defined up to homotopy. In fact, even more well defined up to isotopy. And so, in fact, you get a representation from fundamental group of B to the modular group of the fiber, which is called the monodromy representation. So this is a representation from fundamental group of B to the modular group. So here we have a genus G holomorphic family of curves, so to the modular group of genus G. And in fact, what we are going to see is that for a truly family of holomorphic curves, in fact, this representation is very rich. So, for instance, what we are going to prove, and I hope we get to this result, that this representation is irreducible in the sense that there is no multi-curve which is invariant by the representation. Okay, and this will be one of the very important ingredients to prove such a statement here. And also, the image of this representation is an infinite group. Right? And this is not at all a trivial statement, so I think we are going to spend all the lectures to prove this statement. And then I hope that I will be able to explain why we can deduce the geometric monodromy conjecture from that. Okay, so the thing is that the proof of this theorem, so there is in fact, unfortunately, I have not read the paper of Manin, so I don't know what the techniques are in this paper. So I followed the exposition by Macmillan, as I said. And in fact, the proof I am going to give uses analytic properties of Teichmüller spaces. And so now I am going to try to make a kind of survey of these analytic properties. So what is the definition of Teichmüller space very quickly, and then what is the analytic structure, holomorphic structure on these Teichmüller spaces, and then I think we will stop for today, and tomorrow we will continue on that, and maybe prove use these properties. Okay, so so maybe so let me recall. Definition of Teichmüller space. So maybe I should say something before going into this Teichmüller theory review. Is that, in fact, we, before all these things, so Manin and what I'm going to cover, we knew very little, I think, about monodromy this monodromy representation, apart from something which was very well known, which is, so in all the algebraic families of examples that we described till now, it was algebraic families, and in fact, there are algebraic families of smooth curves, but there are some finite number of curves that become singular. And in fact, there is a well-known theory which comes back from Picard and Lefschetz, which describes what is the monodromy of your family when you turn around a singular fiber. And so this is kind of interesting. I will just say what happens and not prove anything, but just I think this is really important just to have this in mind. What happens when a curve becomes singular? I think there is so there is an annulus in the varying curve, which becomes to a point, and in fact this annulus is called or a cycle in this annulus is called a vanishing cycle. And in fact, the Picard-Blechet's formula tells you that when you turn about the singular curve, the monodromy is going to be a right-handed Dehn twist along these vanishing cycles, right? So you have just I'm going to just state the things or. So when you have a singular fiber, and when you go, so when your B parameter tends to a parameter, say, B naught or Bs corresponding to a singular fiber, so above Bs, say I'm considering a family of a subfamily of curves in the pencils I described before. So what we get is a singular curve, and the picture is like that. So you have a certain annuli here on the smooth curve, which is going to shrink to a point here. And in fact, when now you make your curve turn around the Bs parameter, so the B parameter lies in a complex curve, so in a real surface of dimension 2, you can turn around the Bs, so the singular parameter. So when you turn around them, what you get is a monodromy transformation, which is identity apart from the annulus, and in the annulus, you get what is called the Dehn twist. So namely, so I am going to represent my annulus like this in the plane. So what is going to do a Dehn twist? Is going to map these curves here to the curve turning around here and going once around and getting out from the annulus in the same position as before. So you have this family of curves which are replaced by this Dehn twist by this family of curves. And in fact, if you turn, so you see that here the curve is turning on the right. We call that a right-handed Dehn twist. And in fact, the statement is that when we turn in the positive sense around the Bs parameter, we get a right-handed Dehn twist like that. Okay, so this Picard-Blechet's formula is not really difficult to prove. In fact, we just have to remark that apart from the node of the singular curve, we have a trivialization because we have a fibration. So the map is a submersion. So apart from the singular point, we really have a fibration. So of course, the monodromy is going to be the identity apart from a small neighborhood of the node. And then we just have to make an analysis of what happens at the node. And so this, you have to enter in the formula. So you have to get a normal form of the nodes, etc. There is a small argument, which is not very difficult. And you see that you get this Dehn twist as a monodromy. OK, so but here, so the goal is going to have some more global information about the monodromy representation. OK.
Does the order of the degeneration affect what monodromy you get?
So here,
some polynomial is vanishing.
you mean do the type of the singular points? Yeah, in fact, you are right. There is a kind of so to get this statement, you have to, yeah, you're right. You have to assume that in some sense this this singular fiber is non-degenerated in the sense that, okay, so this is, you're right. It was kind of not very precise here. So this statement applies, yeah, sorry, for what is called for left-shade fibrations, where here at the neighborhood of a node here, so in a left-shade fibration, you might have singular fibers, but at the neighborhood of the node, the map pi is just defined by pi. In some coordinates, you have the simplest singularity that you can expect. So you have a most critical point. Right.
Can I ask you?
Yeah.
Why does it depend only on the homotopy class of the loop?
Because
not this example in general for this proper submersion.
Right. In fact, so the thing is that you can trivialize the fibration locally. So you locally see that your the map pi is locally a product. So locally you have a product structure of the space. So say, if you take a fiber of your space X, of the fibration, you have a neighborhood of that fiber which is really a product, and where the fibration is just projection on the B coordinates, right? And so no, I don't say you get. So I think your question is, I don't say that you get a map from pi 1 of B to the diffeomorphism group of a fiber. I mean that you.
I believe that if you have an actual loop, you do get a diffeomorphism.
Right, you get a diffeomorphism.
Why does it factor in?
But you don't look at this diffeomorphism. So this diffeomorphism will not give you a representation a priori because, as you say, you don't have any connection on this fibration. But you look at this diffeomorphism mod homotopy. So you look at in the modular group, and then in the modular group is well defined. So namely, in the modular group, it is true that the element you get, the monodromy you get, is well defined and does not depend on the homotopy class of the base loop.
But why?
Yeah, I don't. Yeah.
If you concatenate for two parts, they bound a disk, and so you can make a two-parameter family of holomorphic isomorphisms, and contracting the path will give you your homotopy between the two.
Yeah, maybe this is what you say. A fibration over a disk, I mean, a submersion, proper submersion over a disk is a product. If you believe that, so then, then in this trivialization, your two trivialization over the two passes, as you say, gives you some. But you have to prove that. I mean, this is you have to prove something, of course. But yeah, it's non-theorem, but yeah, but he wanted to know that. Yeah, that's right. I can say that. But let me just try to go.
So using that as holomorphic map somehow. It's not just.
It does not use holomorphic things. It's just a statement about you have a fibrate. I mean, you have a proper differentiable fibration. You have a proper summation, it is differentiable, not holomorphic, over a base. So then you get this representation. You get a fibration locally, and you get a representation. This is really not something which is holomorphic.
What's the Lefschetz vibration under
So Lefschetz vibration. So okay. So here also, so Lefschetz vibration. Okay. So it's. I would just wanted to say something. So the true definition is that you have a map from a complex surface to a base, right? Which is proper, which is a summation apart from a finite number of critical points where you which are non-degenerated, right? So those are Morse points. So the second derivative is non-degenerated, right? So you can write the map locally at neighborhood of critical points in this form, right? And these are for those Lefschetz vibrations. So of course, if you have a Lefschetz vibration, you have a holomorphic family of curves apart from the fibers containing critical points. But you also have some critical, some singular fibers, a finite number of them. And this statement was for something related to the neighborhood, to understanding the monodromy at the neighborhood of these singular fibers, right, for Lefschetz vibrations. Okay? I just wanted to just say that we know what happens for the monodromy the neighborhoods of these singular fibers, but we don't really know what happens globally, and this is the subject of my lectures. Okay, so how much time do I have now?
10 minutes.
10 minutes. Okay, so let me just define Teichmüller space and review some properties of these spaces. So I'm going to fix a genus which is going to be at least 2 most of the time. If not, I would say it. And as a set, the Teichmüller space is by definition the set of couples of compact Riemann surface of genus G plus a marking. I'm going to tell you what is a marking in 1 minute. So X is a compact Riemann surface of genus G, and X is marking. So to say what is a marking, I have to introduce first what is called the reference, what I will call the reference surface. So which I am going to denote by SG, the reference surface. So closed, oriented surface of genus G. And a marking is a homotopy class of homeomorph from SG to X. Right. Marking is a homotopy class of homeomorphism, criterion orientation, and I will denote generally them by phi from SG to X. And I have to make a quotient here, because of course if I consider the set of all Riemann surfaces, all marking, it's going to be too much. So the equivalence relation is that if So to simplify notation, I'm going to make the convention that if you consider two marked surfaces, so x and the marking of x, m, as I'm going to denote by mx, it's going to be equivalent to y, my, if and only if there exists H, a biolomorphism from x to y belonging to to this class of maps. So here we have a class of maps well defined up to homotopy. Inverse says that we take the set of all inverses of this class, Nx. And we can compose two classes. This is a set of all compositions of one element of this class and one element of this class. Right. So this is a. So of course we are going to identify two Riemann surfaces if they are biolomorphic, but also we want that this biolomorphism preserves the marking in the obvious sense. So this is the set. So the first thing that we have to do when we are going to, when we want to make to use this space is to how do I do that? Okay. So what is a topology? So to define the topology, let me recall a very famous and important theorem, which is the uniformization theorem. And let me just put one because we are going to use tomorrow another one which is more useful for our goal. So this one is due to Poincaré and Koeber. So this is that every compact Riemann surface of genus at least 2 is biolomorphic to a quotient of the unit disk by a lattice in its homomorphism group. Biolomorphic to a quotient of the unit disk. So the set of complex numbers of modulus less than 1 by the lattice in its group of automorphisms. So automorphisms means biolomorphism here. And since it is compact, this lattice is going to be uniform, and such a lattice is called in general the Fuchsian group. And so this theorem is extremely interesting in the sense that we know that there exists a very symmetric metric on the unit disk, which is given by this formula. So this is called what we call the hyperbolic metric. So it is a conformal metric on the unit disk. Its curvature is constant, equal to -4, I think, in this example, in this representation. And it is invariant by the group of automorphism of the unit disk. And so this theorem, uniformization theorem, tells you that every compact Riemann surface of genus at least 2 can be considered as a Riemannian surface of constant negative curvature. And so, so this is very important fact. And so and this permits to define a certain number of functions on this set, Teichmüller space, which are going to define the topology. And the idea behind that is that, in fact, we have, so it's possible to prove the following thing. So the idea behind what I'm going to say now is the following fact. So suppose you have a holomorphic families of curves. So let me just draw them as surfaces. So they are just to draw that their geometry is varying. So let's just assume that the genus is, as in the picture, say 2 or more. And so on each of them, you have a Poincaré metric, the hyperbolic metric coming from this uniformization theorem. And in fact, just do that, try to do that. You can prove that this Poincaré metric depends continuously on the parameter. Okay, so you get, in particular, you get, say, a metric on the on the tangent bundle to the vibration pi. So, on, say, the kernel of the so this family of hyperbolic metrics defines a metric on the kernel of the vibration pi, and the statement is that, in fact, it depends continuously, and even more, it's analytic, in fact. And so to define a topology, it's natural to look at this metric. And so, so let me just find these length functions on Teichmüller space, and then I'm going to stop. So just define the set C. So consider the set C of homotopy class of loops, classes of loops from, so continuous map from the circle to the reference surface SG, right? So you look at all the homotopy classes of curves in SG, loops in SG, and if you take any element, so any homotopy class on this reference surface, so then you get a certain function LC defined on Teichmüller space with values in, say, 0 plus infinity, which is just the following. So LC of xm, by definition, is just the length of the geodesic homotopic to phi of C. So where phi belongs to the marking. Okay, so you push your loop by the marking. So your loop is defined up to homotopy. The marking is defined up to homotopy. So you get something which is well defined up to homotopy. So you get a loop on X, which is well defined up to homotopy. And then you look at the geodesic in its homotopy class with respect to the hyperbolic metric related to X. And so there is something to prove because, of course, a priori, it that there are many geodesics in this homotopy class, but since this metric has negative curvature, there is only one geodesic in each of homotopy class up to reparametrization by time. And so the length is well defined, right? So, so you get some functions defined on the Teichmüller space. Of course, if you have this picture in mind that I just described before, you expect that these functions are continuous. and you just define the topology by saying that this is taking the topology defined by these functions. So preimages of open sets by a certain number, a couple of these functions defines the open sets for topology and Teichmüller space. Right? I have to stop here, and so tomorrow we are going to define the complex structure on Teichmüller space, and then to try to play with that. Okay, thank you.